so last time we talked, or let's see, last time we had intended to talk about simplicial maps and that sort of thing. We got sidetracked talking about homotopies, that's what today's section was on. So I'm going to circle back and talk more about simplicial maps and what they do in homology. And there'll probably be some more discussion about homotopies thrown in there as well. Okay, so simplicial maps. The idea is if I have a simplicial complex, so let's let x and y be two different simplicial complexes. So I've got them there. What are they? They're a collection of subsets of potentially two different sets of vertices, but that's totally fine. So a simplicial map is a function this notation is a little opaque, but I mean a function as sets. So it's just a function taking simplices to simplices clearly. Such that f of, f of some simplex, this is an n simplex, is n simplex, y. Obvious point to note here is that this is an n simplex in x. So give it as input an n simplex, it gives me back an n simplex. And if simplex, let's see here, I've got one simplex as a face of another. So let's say, I don't know, sigma is a face tau in x, then f of sigma is a face f of tau in y. Okay, so given these two constraints, that's what a simplicial map is. Okay. So it's a function on simplices, takes simplices to simplices, preserves their dimension, and preserves their face relationship. Great. If you look at this, you can see what this is really doing. This is really acting on the vertices in some reasonable fashion. Okay. So you can see right off that f automatically is a function on the vertices, taking each vertex in x to each vertex in y, and the vertex relations get dragged along for the ride. Now, given this kind of structure, this does something very nice to the simplicial homology of x and the simplicial homology of y. So, what does this do to simplicial homology? Well, it does something nice. Is your computer going to take off?
You know, okay. I don't know. I opened it originally to try to submit, but it decided it wanted to die close on me.
Heat up the room. Okay. All right, so what does this do to simplicial homology? Well, the way to think about this is it does something on the level of chains. So it works on chains and produces a chain map, and I'll explain how. So, in particular, we will prove the following proposition. If f from x to y is a chain map, is a simplicial map rather. Then this induces a chain map linear map. This second and we've already proven once we've got a chain map. So this statement here this follows. This follows from what we proved with your chain maps. And in fact, assuming you're submitting tonight, you have code that computes these things. Okay, so the moment you've got simplicial maps, by the end of this lecture, we'll know that they, in fact, induce linear maps on homology, which means that somehow homology is reflective of changes that occur on the simplicial complex structure. Okay, now I need a little bit of technicalities to set this proposition in context. Give you some examples, and prove the proposition. And Dave, you arrived at just the right time because I haven't erased it yet.
Okay, you can start erasing. It's my fault.
That's fine. Take a snapshot. It's also on the video. Got it?
Yeah.
Okay. It's on the video?
Yeah, I was just interested what it.
Okay.
Yeah, looks good.
Okay. All right. Okay.
Are you ready for your close-up?
I'm never ready for that. Then again, I'm a mathematician. So, most mathematicians don't even aim to get dressed, I don't know, nicely. So, as it is.
What's a good modifier?
Tell us how you really feel.
Anyway. There's something here. Okay, so I want to first give you examples of simplicial maps to stick in your head so you can say what they do. And then we'll realize what we need to do to unpack this word here, the induces word. Induces is kind of a loaded word. It shows up a lot in category theory, and that's kind of what I mean. I've said the word category theory a whole bunch of times. Told you what categories are. Induces has to do with the existence of certain functors, which is what's going on here. So we'll unpack that and make that very explicit. All right, but first order of business is to give you some examples to stick in your mind. Okay, so the first example is this kind of thing. So here's a simplicial complex. Let me label the vertices for you. There we go. I'm trying to maintain consistency with myself. So here's a simplicial complex X. I've got another simplicial complex Y. Notice there are two different vertex sets. This one's got a 2 simplex, and the Y here doesn't. Okay? And here we go. I'm going to map Y into X. So I'm going to build my simplicial map. Like so. Okay, so what I'm going to do is I'm going to take A and map it somewhere, take B and map it somewhere, take C and map it somewhere else.
Why are you going from Y to X? Just because.
Just because. Do you want me to call them X and Y?
Yeah.
All right. Very well. Is that better? Do I need to move that one over to the other side?
No.
All right. So I need to tell you what's going to happen to each of these various simplices, because remember the simplicial map is on the level of each of the sets. So in particular, let's name this simplicial map. F maybe? Okay. So f of, well, various things. So let's say f of A, let's take it somewhere. I'll take it to 2, for instance. So simplex in, simplex out, preserves dimension. Let me tell you where B goes. B goes to, say, 3. And C goes to, I would say 4 for the moment. Whoops, C goes to 4.
We're defining this to be so.
I'm defining it to be so. Yes, indeed. So I'm defining it. So, let. Now, once I've specified this amount of information, the axioms of simplicial map drag everything else along for the ride. First of all, I have to take my edges to edges, and I've got to preserve the face of relation.
So would AB go to 2, 3?
AB goes to 2, 3, precisely. Right. So these is all, sort of, these are the, this is an independent specification. And then this, from here on out, that's going to be the dependent specification, which is to say, the moment I've set this, this comes for free. So, for instance, AB turns out to be 2, 3. F of C turns out to be what? 3, 4. And F of AC happens to be 2, 4. And that's all there is to it. That's a complete specification telling you where all the simplices on X ended up in Y. Okay. Now, I made this claim about chain maps, so let's see what happens when I do that. Well, if there's chain maps involved, there ought to be multiple chain complexes, and they have to, in some sense, be based off of all this machinery.
No one gets mapped to 1?
What's that?
No one gets mapped to 1?
No one gets mapped to 1. Going this way, this thing got squashed over there somehow. And 1 is just outside the image of this function. As is the simplex 1, 2, 3. That's also outside. Okay, so let me specify the chain complex for X. Let me specify the chain complex for Y, and let's see what happens. The chain complexes for X and for Y initially don't have anything to do with one another. So I start off with C0. In fact, what I'll do is I'll put the degree up top for you to reach. In degree 0, these are the C0s. C0x, that's what? That's the vector space spanned abstractly by all the vertices in X. C0y is spanned abstractly by all the vertices in Y. So what dimension is it?
R1. Isn't it?
What? C0 of X.
No.
3. I have 3 vertices.
I'll think about homology, not.
Yeah. We're not there yet. All right. And then in Y, it's R4. Now, at this point, it's going to be really useful to keep track of who's who. We want to make sure we don't lose track of the fact that 1, 2, 3, 4 might not be in the order 1, 2, 3, 4. Let's keep sanity for the moment and label the dimensions here, A, B, C, and 1, 2, 3, 4. That will become apparent as soon as I write down the boundary matrices. All right, so here's C1 and C2. All right, so how many edges do I have over in X? 3. So that's gonna be that's gonna be an R3. And how many two faces do I have in X?
5. Oh, sorry.
In X?
0.
Yeah, 0. Okay, so I need to specify one boundary matrix here. I'll do that in a moment after I get the plan laid out. Now what about on the other side? The one chains the edges, vector space spanned by all the edges over here in Y. How many are there?
R5.
Yeah, there are 1, 2, 3, 4, 5 of them. This is going to be R5. Now, how many two-dimensional faces are there over here?
1.
Just one. And then there's nothing else. And so that can map to 0, and of course that can map to 0 for C3 and higher. Okay. So I need to specify then two boundary matrices. And then, well, I've argued that this thing, this F, this simplicial map, is going to induce some kind of chain mapping going down, and that's where the vertices to vertices, edges to edges constraint is important, because if I had vertices mapping to edges, well, it would kind of do something like that, not a chain map anymore. Or if I had edges mapping to vertices, well, something like that going on, that ain't a chain map. So, all right, let's fill out everything here. Now I'm going to use a bunch of different colors here, keep track of things. Homological algebra cannot be properly done in a single color, as far as I can tell. You tell that to publishers. All right, so
Probably need at least 4 colors.
no, usually 3 is good.
Those,
I know, it was a bad reference to 4 colors. But it's completely irrelevant. No, my board up in my office after a bunch of office hours had probably upwards of 6 or 7 colors, I remember. Quite a few. Anyway, that was some intense homological algebra going on. Anyway, so the columns of this guy here are the different dimensions of C0, i.e. the vertices. So I'm going to label the columns with vertices. So I've got 1, 2, and 3. I'm going to leave off the brackets or things are going to get really nasty. All right, now the rows of this matrix come from the A, B, and C, gosh. All right, A, B, and C, and the rows are the edges. So I've got, let me do them in lexicographic order, A, B, C, B, C. Okay. That's the zero metric, so I don't need to do anything with that. Now down here, let's do it all at once. I have 4 vertices. 1, 2, 3, and 4. Again, lexicographical order. What edges do I have here? You know what lexicographical order means?
you mean in alphabetical order?
1,
Yeah.
2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4.
Lexicographical ordering means, yes, alphabetical order in some sense, but
Almost like sort of binary moving up and keep your...
kinda, yeah. Yeah, so it's like dictionary order, or this is dictionary order, or as we say, alphabetical. For whatever reason, computer scientists call it lexicographical ordering. I don't know why. Exactly, probably because the fancy Greek word is amusing to people. All right, so what do we got? We got 1, 2 for sure. That's in there, that's this edge. Then 1, 3. Then 2, 3, 2, 4. And 3, 4. And that's it. This matrix has got all of these guys, and they all have one row into the 1, 2, 3 simplex that's there. 1, 2, 1, 3, 2, 3, 2, 4, and 3, 4. Okay. Now, the color, we'll block this up. Just to keep track of things, I always find drawing in the grid lines prevents errors later. Now, let's see, these are just for the chain complexes, so let's fill them out. So, there +1, -1, or 0 are the possible entries. 0 if they have nothing to do with each other, +1 or -1 depending on the order. So, let's see here. A in AB. Wait, am I going backwards in dimension? Huh, I'm doing cohomology. Funny that, I didn't even notice that. Oh well, never mind.
Oh yeah, we
It's
swapped
just
it.
swapped, right?
Yeah, we swapped it.
Everything inside is transposed from what it should be.
Yeah.
Okay, I'll fix that. All right, folks, we're doing simplicial cohomology. Don't let that bother you. Okay, all right.
Coaching.
Cochain complex. That means everything's been transposed. Sorry.
So we need to transpose all these matrices?
No, I just
To
switched
get
it so
back
we
to where
don't.
we were, we just have to look at them differently.
You just have to, so if you transpose the matrices, then if I take a look at this matrix and I transpose it, sorry, this is a point I didn't want to get into, oh well. If I transpose this matrix, what happens? Which space is its domain? Well, its domain was here before, and its range was here. If I
Right,
switch
so
the
now
rows
we-
and columns, it goes the other way.
Right, new domain would be.
Right. So if I transpose this matrix, I'm going that way. If I transpose this matrix, I'm going that way, etc. Transpose this matrix, I go that way, this matrix, I go that way.
And we want to be going down.
And we want to be going down in dimension. And I'm always backwards of what I ought to be anyway. Cool. Doesn't much matter. Actually, for this particular construction, it matters not at all. In particular, super deep theorem that homology and cohomology are very, very related to one another. And there's something called Poincare duality that usually crops up in many cases. And there's a whole host of duality theories that link up these various complexes with one another.
Could you define what cohomology is?
It's the same exact thing. It is the homology of the cochain
Like
complex.
co-kernel?
Yeah, what's
Wait. We talked about co-kernels.
Yeah,
It's the kernel of the transpose map,
oh, okay.
in fact. That's exactly what it is. If you take the transpose and compute the kernel, that is the co-kernel. Anyway, for what I want to show here, nothing is going to be any different. Okay. So, all right. I'm asking now for the boundary of AB. What's the boundary of AB? In terms of A, which of these entries did I have to delete? The first or the second?
Second.
The second. So it comes in with a
-1,
-1. Yup. And what about this one here?
1, 0.
That's a +1 and a 0. And then here I do a what?
-1, 0, 1.
I get a -1, 0, 1. Yup. And this one?
0, -1, 1.
0, -1, +1. Yeah. Okay. Notice it's basically the same as before. Now, down here, same kind of thing going on. What do we got?
-1, 1, 0, 0.
-1, 1, 0, 0. Yep. And then -1 again, 0, 1, 0. Okay. 0, -1, 1, 0. 0, -1, 0, 1, 0, 0, -1, 1. And what about over here?
Negative,
Plus minus plus. So this is a +1. Plus minus, that's a -1. Plus 0 and 0. Okay. So again, if we were filling out this as homology, it would have been the same sign pattern, just transposed. So we're good with that. This is that same boundary map going on. Okay, great. So now what do we have? We have this simplicial map, and it's translating vertices into vertices, edges into edges, other things into other things. Well, I've got vertices over here. They are the various dimensions of this, and they translate them into vertices. So our F map literally translates vertices to vertices, edges to edges, other things to other things. So it should be a matrix as well. What shape should this matrix be?
4.
How many rows should this matrix have?
Oh, I was
5.
4.
I'm talking about this one here.
Oh, 4.
4, and how many columns?
3.
Great. Right, the columns should be labeled the same way as I've got over here. A, B, and C, and 1, 2, 3, 4. And then basically the same kind of things going on here. This should be a what shape matrix?
5 by 3.
Yeah, 5 by 3. Here they go. 1, 2, 1, 3, 2, 3, 2, 4, 3, 4, and this is now AB, AC, BC. They are labeled with edges. Okay? Now, the great thing about these matrices is they're really easy to fill in. You don't have to do any counting or anything. All you need to do is put in ones where that's what the map does and zeros otherwise. So, where does A get mapped?
To 2.
A gets mapped to 2. Where does B get mapped?
3.
And where does C get mapped?
4.
Yeah.
4. And zeros everywhere else. Okay? Now what about over here? Where does AB get mapped? 2, 3. Where does AC get mapped?
2, 4.
2, 4. And where does BC get mapped?
3, 4.
3, 4. Aha! And zeros everywhere else. All right. And this is like a big fat zero map. This is a, what shape is this map here? This is a
1 by,
1 by 0.
1 by 0 matrix. So 1 by 0 matrix. Still 0 matrix. Okay, so this is the structure of things. And so now all we would need to do to check to see if this is a chain map is do a little bit of multiplication. What do we have to do? Chain map? Yeah, how do we check? Yeah, check if this is a chain map.
exactly 0, 0, kernel,
No.
Would it not be,
Civic.
isn't it not because I can already, like, the top line, R3 to 0, then goes down to R, that doesn't make sense.
Wait, from here?
No, from C1, like, there, that gets me, that stays at 0 the whole way. But if I go the other way, I may not necessarily get a.
Yeah, does this break?
I mean, I don't think it would be a mapping from 0 to R, would there? Because there
Well,
are,
it's just a zero map, so,
I mean, because wouldn't that not?
so let's see, did I get this completely backwards?
Yeah.
Yeah, did I get this backwards?
You're saying we should have the arrows pointing up or
what
something?
do we chain that?
So I am multiplying this matrix by this matrix, right? So row into column, right? So this row into this column, this row into that column, this row into that column. That particular 2, 3 seems to be giving us trouble, huh?
Yeah.
Was it the first?
Because you get a 1.
Yeah.
Should be a-
Indeed, indeed you do. Indeed you
Might it be because we can't necessarily map from
do.
that simplicial map to that simplicial map because they're not the same, they don't have the same Betty numbers?
No, that should be fine. Well, let's see whether or not I was completely wrong about the cohomology versus homology game, huh? So if I go this way, there's no trouble, right? If you transpose this matrix, that matrix, and of course this one, does that work then? Well, 0 maps to 0 maps to 0, 0 maps to 0, sort of trivially so. And then what about going this way? So if I take this matrix after this matrix, I get a 0 up top, and the 0, aha, so it seems to work the other way. Really, are you telling me that simplicial cohomology is a contravariant functor?
I mean,
Maybe.
we're not telling.
You're not telling me. The math is telling me. Okay, so given that, okay, how quickly can we compute transposes? All right, teachable moment here. Transposes in software are hard to compute because they involve a lot of copying.
Should we just put capital T's above all our?
Well, yeah, but then it's kind of hard to do the matrix multiplications.
I'm gonna. What you trust?
Yeah, you can do that. You could do that.
The matrices are so small on my paper to like erase, it would be erasing the whole thing.
All right, okay, fine. So basically what you're saying is this failed.
Use our imagination.
No, let's not use our imagination, let's do it correctly. Let's do this.
I imagine this math could be correct, therefore it
No,
is.
that's wrong. No, don't do that at all. Don't do that at all.
That's life and that's math.
All right.
Sometimes you waste paper.
Sometimes you waste patience. All right. Sorry about that. Actually, no, I've got to ask myself.
Jesus Christ. Mr. Roberts, look at my little diagram.
This falls in the category, note to self, read the notes, it was done correctly in the notes. All right.
Wow, that's impressive. Now I'm just gonna make a whole big page for this.
So recycle bin for one.
Recycling bins. Recycling bins. Anyway, all right, so.
So should all our arrows be pointing from?
Not
right to
these.
left?
These are right.
No, but everything should be pointing from right to left.
Yes, that way. Down in dimension. All right, so I should have a matrix going, let's see here. This one went from AB, C, B, C to 1, 2, 3. That's the output as such. No, to ABC, right? Still. Okay. Here, this is going from 1, 2, 3 to, no. This one is going what? No, there is no one here. This is 0 math. Okay. This one's a more complicated one. This one goes from the 5 different edges. 1, 2, 1, 3,
It's a 4x5.
2, 3, 2, 4, and 3, 4. And it maps into 1, 2, 3, and 4. It is a 4 by 5, just as you say, exactly. Okay, all right. Next time I start computing cohomology instead of homology, someone should yell at me, because apparently I am prone to making this mistake. All right. 1, 2, 3 goes into 1, 2, 1, 3, 2, 3, 2, 4, 3, 4. Okay. Block these guys up. Block, 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 block. Okay. All right, let's fill this one out. This one here should be a -1 in any event. This one should be a +1. This one should be a 0. This one should be a -1, a 0, and a +1. This one should be a 0, a minus 1, and a plus 1. Okay, got that matrix. Okay. So, this matrix, this should be a minus 1, plus 1, 0, and a 0. This one should be a minus 1, 0, plus 1, 0. This one should be a 0, minus 1, plus 1, 0. 0, minus 1, 0, plus 1, 0, 0, minus 1, plus 1. And this one here, let's see here, plus minus plus. So this should be, wait,
Okay.
plus minus plus, yeah. In this case here, I'm deleting plus minus, yeah, plus minus plus. So this is a plus 1,
Minus 1,
minus 1,
plus 1.
plus 1, 0, 0. Okay. All right, that wasn't so bad. And indeed, this is now a chain complex. Indeed. Let's quick check to make sure that this thing really is a chain complex. 0 times that is definitely 0. We're good. Row into column. Row into column is definitely these two guys 0. Row into column.
Yeah.
Yep. Row into column. Yep. Row into column. Yep. Okay, good. So is chain complex, is going in the right direction, so it is a simplicial chain complex. All right. Okay, still the same chain map. Ostensibly, now let's check to see if it really is chain map.
The first,
First square
commutes-
certainly commutes trivially,
Yeah.
because 0 times anything is 0 times anything else. Yay. All right,
Yeah.
now. Row into column.
0.
All right, so now let's actually write these out. Yeah, this is going to be sort of obnoxious.
You need a computer.
Need a computer. Someone want to type this into NumPy? No, not really.
We have code for this, right?
We do actually have code for this. Actually, we actually do have code for this. All right. Let me at least verify it myself that this actually comes out right. If I multiply the first row of this into that first column, I get 0, which is indeed 0 times 0, anything, yes, okay, good. That's at least is doing something reasonable. If I hit the, say, the second row into the first column, that would give me a minus 1. So second row, first column. Second row, first column, got a minus 1. All right. Not that two agreements work, but I think that's right. Okay.
Might want to edit this out of the video.
Okay. You hear me making the wrong statement, but this induces a chain map on homology complex. Oh well. Ah, yes, actually then the arrow, then I do have to transpose the stuff in the middle. That's what we're wrong. Okay. All right. Yes, because then my chain maps actually kind of go the wrong way. All right, anyway. All right, so that's kind of what's going on. Now, what we want to do is we want to show how this is going to play out in terms of the theory. All right. First of all, does everyone understand the construction? Does it make sense? The chain map is basically drop in a 1 wherever the thing mapped. So in particular, for each column, there will be exactly 1, 1.
It's a chain map.
Good. You checked all of them?
Yes.
Wow.
It's just linear algebra.
Well, of course it's just linear algebra. Then again, I'm up at the board. All right,
It's a lot of linear.
it's a lot of linear algebra. It's just 1s and 0s and such.
Yeah.
That's a lot of
Because it's all 1s and 0s.
It's still a lot of
things cancel nicely. Cool.
Okay, anyway. Right, so once you've got a chain map, then we're good to go. So now what I need to do is I need to set this in a theoretical context. I'm going to set this in a theoretical context. And in particular, so first of all I want to say, actually we want to go after this proposition. So let's look at this proposition. The thing that we needed was we needed the induced part. the induced part means is it means that every time we have two simplicial maps. You just x to y and y to z. So, of course, this is G composed with F. Every time we have two simplicial maps like this, every time that occurs, we also get two chain maps. Again, this statement here we get is yet unproven, generally.
But you mean, we haven't proved it or no one?
No, we have not proven it.
Okay.
Yes. Yes, we've got an example on the board now that actually apparently works. And we will prove that in a moment. But what I want to do is you could literally take this and map to some random chain map and say, well, there we go. But it doesn't do anything nice. What we want is we want to get these two chain maps that respect that composition. So I'm going to get two chain maps and they're going to go chain associated with x, chain associated to y, and chain associated to y to z. The important part here is that this composition is respected. So let me call the process of constructing the chain map for F, I'll just call it CF, and here's CG. And the point is, this is the induces part, such that C of GF is equal to, importantly now, CG composed with CF. Looks like I just moved the parentheses around, but this is actually important. This is saying that I could either construct the chain map first of each of them, and then compose them as two separate chain maps. Or I could compose them first and do the chain map. This is saying, in a nutshell, this process of constructing this chain map from the simplicial map respects the structure of simplicial maps. So this respects composition or structure of simplicial maps. Important. What happens if I put F or G as an identity map? What should happen?
Reduces to the other one?
Yeah, it should reduce to the other one and somehow say that I've picked a chain map that somehow does something useful in the sense, or rather does nothing useful really, as in I've taken my space and I've perhaps relabeled it. Does the same thing, didn't really change anything, it shouldn't really change anything on the other side. Okay, now let me ask you quickly, is there always an identity simplicial map? Can I take all the simplices and leave them alone? Is that a valid simplicial map by our definition? Well, take simplices to simplices, edges to edges, preserves the length of each of these lists. Yup. Does it preserve all the face relations? Yup, so it's a simplicial map. Now, okay, what if I take this composition of two simplicial maps here? I've implicitly thought that the composition, is that also a simplicial map? Well, this took, say, a simplex of certain length to another simplex of all the same length. So this takes, say, a simplex of dimension n, turn it into another simplex of dimension n, turn it into yet one more simplex of dimension n. Preserve the face relation, preserve the face relation. So composition of simplicial maps preserves the simplicial mapness. So in particular then, this means that what we've got is we've got a category of simplicial maps. And what this is saying, and this is, if you want to be fancy about it, this says the process of computing the chain map from the simplicial map is a functor. It preserves all of the structure that you would want to have about the simplicial complexes and their relationships, and turns it all into linear algebra. Lots of linear algebra. But then from there on out, we can just do linear algebra. Yes?
Just a notational question.
Mhm.
So that process of computing the chain map you're representing with a C, did you mean for there to be a C in front of that parenth Y?
Where? Here?
Just down?
Yes. Yes.
Solid.
That should be a C with Y. You're absolutely right. That constructed the chain complex. Here I've got now, this is really, then C of F is now in here. Is now all the stuff in the middle by this notation. These various component maps are getting dragged along. Okay, and the point is that these things, by our earlier reasoning, when we find that that's a chain complex, and this is, or rather, this is a chain map, i.e. all the squares commute, then it induces, by this same kind of machinery, maps on the homology. Yeah.
So if you put another one down the bottom, it
Yep.
went straight from the top to the bottom, it would be
Yep.
same as going from the top to the middle to the bottom.
Exactly. Exactly. That's in fact what's going on here. And furthermore, if I did this by taking the maps on the simplices, take the maps of the simplices from the top to the middle of the bottom and compose them in one go, that's the same matrix that I would have of ones and zeros when I go to the top to the bottom.
Wouldn't it be the zero matrix?
No, not necessarily.
Because if you're composing two adjacent.
This direction, along this direction, these guys here, these are the chain complexes. These are not chain complexes. These are not chain complexes at all. And in fact, by computing homology, what we're doing is we're taking these chain complexes and we're sort of peeling out another layer that now nothing's a chain complex, but I have just maps going vertically. The various induced maps that your code should be computing. All right, so I need to now address this. So we've set this in context, I now need to address this thing. So that generally speaking, I get chain maps. And I can compose them too. So I need to first of all give you the general construction of this guy, that's easy, and then show that we get this composition going on. We get actual chain maps. Okay, so here we go. I'll write out what I need to prove too. Okay, so first of all, I need to prove that construction of CF from F yields a chain map whenever F is a simplicial map. And then the second point is that composition of simplicial maps commutes with that operation of turning things into chain complexes. So it commutes with C, that's this equation here. Oops. Okay, so that's what I need to show you. And then we'll be in a situation where, given any simplicial map, we know exactly what to do with that on the level of chain complexes. Okay. Of course, the benefit is then that we can think of simplicial maps in a little bit. We can think of them as sort of the canonical structure of how to think about simplicial complexes being related to one another, because you're relating all the internal structure, the vertices, the edges, and the faces, in a way that preserves all the vertices, edges, and faces. So in particular, if I relabel all the vertices, edges, and faces, that's a simplicial map. So I can think about things up to that kind of regard. Okay, so let's address this. So first of all, let me give you the formal construction. So recall, CK kx. I'm going to now start breaking out the indices. This is, what is it? It is the vector space spanned by k simplices of x. This is the vector space spanned by k simplices of 1. So, let's see. Well, I know what each of the various simplices are going, what's going to happen to each simplex in x. It gets mapped to a simplex of the same dimension in y by f. So, let's see here. Let me take an element in here. Let's say, let V be in ck of x. So, V is, well, what is it? It's a vector space spanned by simplices of x. So, we call that sigma with dimension of k, sigma equal to k. To some of these things, there's a bunch of coefficients. Call that little c maybe, or we call it a of sigma times sigma, abstractly. This is a simplex, this is a coefficient, taking a linear combination of simplices with various coefficients. So this is an abstract vector space built up in that way. Okay? Well, I want to map this thing over to here. Well, let me just define it. CF of that thing. What?
A?
A is a coefficient. So A is in A sigma is a real number. And sigma is a simplex of dimension k. Because I've got a vector space spanned by those k simplices abstractly, that's what they are. Basically what I'm doing is I'm telling you the A's are the entries of my matrix, and the sigmas are the labels of either my rows or columns, depending on where I happen to be. Okay, so now I need to tell you what this purported map CF is going to do to this vector V. Well, it's linear. I want it to be linear. I'm going to assert by construction that it's linear. So I'm going to take the same set of coefficients. And what am I going to do?
Take f of a sub sigma, f of sigma.
I'm just going to f of sigma it. Yeah, there's f of sigma it. Now, that's still a real coefficient. This thing, though, f of sigma, is a simplex where it's in y. So this thing is a simplex. So this is in x. This guy is simplex of dimension k in y. By assumption, we assume that we preserve the dimension of simplices. Take simplices of dimension k, simplices of dimension k, they just move them over to y. So there they are. Okay, and still real coefficients. So this definitely took us directly over. Okay, that's literally it. That's the definition of that. So now, we need to check, is this thing really a chain map that I've defined here? Well, how do I know if it's a chain map?
Take the composition and see if it equals 0.
Nope, that would be if it was a chain complex. We know it's not a chain complex. What does a chain map have to do?
I commute.
Yeah, commute. Squares have to commute. So this thing is on a certain level, right? What level is this? I should really think of this not just as one map, but as one of lots of them. And which map should this be? At what degree is this map living?
At degree k.
This is living at degree k. So I can think of this as living at degree k. So now what I want to do is I want to take this map at degree k and examine what happens. In fact, you can think about putting the k here. It's actually a little more natural to put it over here. I'm going to put it here. Might want to put it here just sort of for general principle, but it's better to attach it to C so it matches up over here. Okay, notationally that's a little better. Okay, so here we go. So to prove its chain map, I've got to show it commutes. And now, here's a chain map. I've put in a heavy dot to say I'm talking about all of them now. So what do I have to do? Well, I have to show that if I take the boundary and I compose it in the right way, so I take CF, I compose it with the boundary, it should be the same thing as the boundary composed with CF. Of course, that's why I leave all the indices off so I can figure them out later. Okay, so I'm going to start off in degree K, move down. So this is the down movement, and then
K minus 1.
K, no, I'm still in K.
K.
Now over here, I've got K, and this is K minus 1. So the picture, here's CK of X, here's CK minus 1 of X, here's CK of Y, here's CK minus 1 of Y. Here's boundary K. This is also boundary K, but of the other space. This is CKF, and this is CK minus 1F. So if I first do the boundary, then I've got to do the K minus 1 to get to here. Here I'm doing CK of F first, and then the boundary. Okay, so that's what I'm going to check. Okay, so now I'm going to take my definition here and make use of it with the various boundary maps. Okay, so here we go. Cut and paste. B is this guy, sigma in X, a sigma, sigma. Okay, so that's what we know. So let's write out then this side of the equation. There's that, and then I'm going to compute its boundary. This composed map acting on V is really the same thing as just doing one and then the other. I've got our parentheses right. So this is boundary K acting on that thing. The boundary map is linear. Okay. Okay. Now let's look at the other side of the equation. The other side of the equation first computes boundary, then computes now K minus 1. So let's do that. First we compute the boundary. And then CK minus 1 on the same V. Same V. And this is and again, by linearity, I should be able to pull this all in here. Notice this is one dimension lower. So I've got something that is going to act F on the one dimension lower simplex groups that. Okay, so the question really boils down, at the end of the day, to whether or not these guys commute, the F and the boundary, commute on a single simplex. So the fact that we're dealing with vector spaces is somewhat of a red herring. All the linearity pushes you all the way down to this single simplex. And now, we answer that question. How? Well, by writing out what that single simplex is and seeing what happens. And we've only made use of one property of F, the simplicial map, thus far. That it preserves dimension. We haven't used the preserve space relation. We've got to use that now to finish up this proof. So let's focus on showing this. So let's focus in on that. So here we go. Let's let sigma, it's a what dimensional simplex?
Okay.
It's a k-dimensional simplex. So it is v0 up to vk. Okay? What's boundary k of sigma on this side here? Well, it's this formula involving the deletions. 0 up to k, -1 to the I, and then delete. So I want to take f of this thing. Oops, boundary k of sigma. Of course, f is, we're really taking cf of that thing here. That's really what's going on here. This is really c k minus 1 of that thing. So that's going to be linear across this. The c k minus 1 of this thing is really linear. So, let's just assert it so. C k minus 1 of f of this thing. Let me just call it f of each one of these simplices. Now, let's ask ourselves, what are these?
What's F?
F is a simplicial map.
Those are k minus 1 simplices of y.
These are all the k minus 1 simplices of sigma. K minus 1 are all k minus 1 simplices. Subsimplices, or just k minus 1 dimensional faces of sigma. That's what they are. All k minus 1 dimensional simplices that are faces of sigma can be found by just deleting each one of those entries in turn. Oh, well, gosh, doesn't that look very much like this formula over here? This would be boundary k of a whole bunch of various faces here, wouldn't it?
Yes.
Yes, indeed. So, in fact, the point then is that because f preserves that structure, because f preserves face relations, what I can do is I can imagine commuting this thing. So I can ask for this same, I'm going to keep on going with my equation here. Each and every one of these are faces, the ith face of f sigma. Really, that's what these are. These are walking over all the various faces of sigma here, but f preserves those face relations. The only time I see that one face is related to another is when the output. So really, I'm walking over each of those various faces of epsilon. Which that is exactly what this formula asks me to do. And that then therefore establishes that we've got a chain map in general. Questions on this?
What's a face?
Face, take a simplex. It's got a whole bunch of sub-simplices.
Okay.
Those are called faces. So for instance, if I have a filled-in triangle, it has a whole bunch of one-dimensional faces, the edges, a whole bunch of zero-dimensional faces, the vertices.
Okay.
So really all that I'm doing here, because F preserves faces, I'm just walking over the various faces of this. Okay, and that's the end of the chain map proof. Now to show that composition is preserved. It's actually not very hard at all, because if you look at it, under the hood, what's happening is we need that formula again. So
this is 2.
this is 2, or 2. What do I want to show? I want to show that CK of G composed F is CK G composed CK F as such. Now, rather than showing it, or in order to show this, generally speaking, I need to show you what happens, what it does to some vector V. Now, without loss of generality, following the same kind of argument we did right here, I can just show you what happens on a simplex. So we will show this for all simplices. And literally, this is not very hard. What is it over here? Well, it is, what does this map do? What does the CK map do to a single simplex? Where does it send a single simplex?
Another simplex?
To another simplex. Which one? Well, this one. This map sends it to another simplex. This takes a K simplex. This is a K simplex. As is this, another K simplex. Well, what happens over here on the other side? Well, first I'm going to do this one, and this one sends me to a K simplex. And, gosh, it sends me to another simplex. And, well, gosh, that holds for functions. Done. So, and then of course, we're extending by linearity. With no at all trouble. So thus, in the end, we've got our simplicial maps induce chain maps on our chain
What
complex.
does extend by linearity mean?
That means, take linear combinations of everything inside. Basically what I've done is I've told you what happens on a basis, you can figure out what happens on the rest. And then that's the end of the story. So now what we've gotten is we've gotten a very precise transformation that goes from simplicial complexes and maps between those simplicial complexes, i.e. simplicial maps. We've turned them into chain maps, chain complexes and chain maps between them, in a way that preserves all that mappiness structure. It's a functor. And then we've got another one that goes from those chain complexes to vector spaces. So in essence now what we've proven is we've proven from the beginning, take simplicial complexes and maps between them, we turn them into vector spaces and linear maps between them, or some kind of representation as a matter of fact. It's a very precise machine that allows you to think about simplicial complexes as vector spaces. And in particular, if I find now, based on this whole machine, if I have two simplicial complexes, and I don't know if they're the same or not, but I can compute their simplicial homology, and I find that they're different, then I know automatically that they have to be two very different simplicial complexes. And furthermore, there's something a little bit more subtle here. These simplicial maps are, you know, some of them are invertible, some of them, those are fine, but the ones that yield invertible maps, if I go from a simplicial complex here to another simplicial complex, map forward and it's invertible, these bijective simplicial maps that preserve the face relations in both directions, those are simplicial complexes that are indistinguishable from one another, as far as the simplicial complexes are concerned. Those are isomorphic simplicial complexes. What this says, and what we've now proven, the fact that these induces, particularly the composition rule right here, what that says is that says very specifically that isomorphic simplicial complexes have isomorphic simplicial homology. That as vector spaces, we get the same structure. Which means now that statement I just said a moment ago, you can use the structure of those homology spaces to tell something official about those simplicial complexes. In fact, it's a little more subtle than that. We can actually tell something topological about them, not just combinatorial. But thus far, we've proven that homology is a combinatorial invariant of simplicial complexes. And that's a great place to stop. Stop the recording and move on.